Hello, everyone. Welcome to the session on LangChain and Introduction. I'm Lakshmi, and I've got 20 plus years of industry experience across AI, ML, and generative AI. I'll start today's session with an overview of the modules that make up LangChain, and then we will go a bit deeper into these modules using a Colab notebook. I'll also take you through another notebook where we get a LLM to answer questions from a PDF document. So the slide deck as well as the Colab notebooks will be shared in my GitHub repo. So let's get started. So what is a LangChain? It's just a framework for developing applications which are powered by language models. So with LangChain, we can bring in the power of external data as well as the external applications into the world of LLM. So there are a couple of points that we need to keep in mind. So LangChain, as some of you might know, there is a release almost every day. So uh, keep track of the latest changes and then use the latest version because that gives you the power of all the new components or modules that they are bringing out. LangChain is available in both Python and JavaScript. So in this example, I'll be using the Python version and also I'll be using the OpenAI models. But feel free to experiment with the open source models that LangChain supports. I've also shared the links to the LangChain documentation as well as the specific Python and JavaScript documentations. So, what are the modules of LangChain? There are 7 of them as of today. So, first is models, then we have prompts, memory, indexes, chains, agents, and callbacks. So, let's get to understand them a bit deeper. So models obviously are the different types of AI models that LangChain supports. So they have categorized them into three buckets. First is LLM models, then we have the chat models and the text embeddings. So we'll dive deeper into them in a bit. Next comes the prompts. So prompt is basically what we pass on to the module, to the model. So this would include instructions from the user, the context given by the user, the instructions given by the user, and the format of the output. And in real life, we kind of hardly pass them on as hard-coded values. Instead, we use something which is called the templates. So in the prompts, LangChain basically has 4 subcategories, which are LLM prompt templates, chat prompt templates, example selectors, and output parsers. Then comes the concept of memory. So by design, the LLM models or the chains or the agents, they're all stateless. So, but we need the concept of memory, especially when we are having a conversation, right? So we need to store and retrieve data. This is achieved with the help of the memory module. Then we have the indexes. So indexes are basically ways to structure the documents so that the LLMs can interact with them. So under indexes, we have document loaders, which helps you to load a lot of whole different kinds of documents, right? So we could load PDF documents, we could load data from a website, and so on and so forth. We'll see them in detail later. Then we have the text splitters, vector stores, and retrievers. Then we have chains. So chains are nothing but a sequence of modular components or just another chains which are combined in a particular way to accomplish a specific goal. So an important point to note here is that the sequence of calling the components is predetermined in case of a chain. But many times we do have use cases where we know we have to use a set of components. For example, we might need a calculator, or we might need to search the web for some information, and then based on that information we might need to access the Wikipedia for a definition of that concept, and so on and so forth. But the sequence, mm, we may not be able to predetermine, and it might depend on the user's input, right? So in one query the user might just ask for a calculation, and in another query he might ask for a web search plus a calculation, and so on and so forth. So that is where the agents come in. Then finally, we have the concept of callbacks. So when we write a piece of code, it's quite important that we log the outputs at different stages for debugging, or we need to monitor certain variables and certain functions. So this is where the concept of callbacks come in. So before I dive deeper, in case you are using the OpenAI models, you can get the key at the platform.openai.com account/API keys. And what I would also advise you to do is to track the usage of the keys, right? Because sometimes you're so busy coding that you kind of tend to lose track of what is the usage that's happening. So just keep a track of the usage at the account slash usage page in platform.openai.com. So with that, let's get into the Collab notebook. Okay. So here is the notebook that we have, which talks about the various modules in LangChain and how to use them. So for using the various examples of, or for running the various examples, we need a couple of Python packages to be installed. So what I've done is I've kind of done it all at one place. So basically, as you go through the modules or your use case, you might find that you need certain Python packages. And if you're using a Collab notebook, you could kind of go and get it installed here. So the two important things that you need to start with are OpenAI and LangChain packages. And then for using OpenAI, you need a key, and it's best to store it as a env variable, and ensure that if you're putting it into a GitHub or something, you don't check it in. But that's quite a safe way to do that. And for that, we need the python.env package. We have a whole lot of other packages here as well, which is required for the various examples that we have here. So the first step obviously is to load the key. So I have run this whole notebook here in the interest of time. So there are multiple ways you could load the key. So one is you could just set it in a variable, or what I have done here is I have put the env file in the folder called variables, and then I'm reading it from there and then loading it into the required variables. So the first module of LangChain is something that's called models. And as we saw, there are three subcategories there. So first is LLMs. So these are the large language models. So what they do is and just for clarification, I'm using GPT 3.5 here, not GPT-4. But if you have a GPT-4 key, go ahead and use it. And as I said earlier, keep track of the usage as well. So we have these LLM models which take a text as input and they return a text as output. So how do we invoke them? So the first step is to invoke the LangChain, and then you have to specify the model name. I'm using GPT 3.5 Turbo here, and you could set a temperature, to whatever value that you need. If you need specific consistent answers, set a temperature lower, and higher the temperature, higher the variation in the response. So here I'm asking the LLM to tell me a story about animals in 50 words or less. And then I get a response like this, the lion, tiger, and bear were best friends. They lived in the forest and so on, so forth, right? Then we have something called the chat models. So these models take a list of chat messages as input and return as a chat message. So this, I guess, is one of the most common applications of LLMs. Then we have something called text embeddings, which are the models which take text as input and then return a list of vectors or floats. So let's dive a bit deeper into them. So if you're using a chat model, then instead of the OpenAI model that we used with in the previous step, use this model, Chat OpenAI. And with this Chat OpenAI, you will have three different types of messages there. So the system message, which basically used to provide context and instructions to the AI. Then the human message, which is what the user of your chat application will basically type in. And AI message is the response that the uh, LLM model or the chat model gives you. So here my context is, you are an AI bot that can recommend Italian food. So that gets into my system message. Then the human message is like what I, as the user, type in, which is basically, I'm going to Italy next week and want to try out some Italian food. What should I eat? And then we get an AI message. It says that that's great. Italy is known for its delicious cuisine and goes on to recommend some dishes for me. Then we have something called text embeddings. This is extremely important if you plan to use external data in your LLMs. Say, for example, you have a text file or a PDF, or you want to use data from some other source. Then all of these text needs to be converted into the numbers or the embeddings, which is nothing but a vector of floats, which is the floating point numbers. And this whole vector holds the semantic meaning of that text. So to convert the natural language text into these embeddings, we use the OpenAI embeddings. So there are different ways to embed your documents. By documents, I mean, the content that you're bringing into the LLM, either from the variety of sources that LangChains can connect to, or it could be the query itself. There's a little difference in the embedding methods for the documents and the queries. And here I have shown embed query. So this is basically what the user is asking. And I've just put it as a sample query. And then we run the embed query method on that. If it's a document, you would have used embed documents. And then you see that it produces an output of output vector, which is 1536 length. So if you look at the first value there, you see that it's a floating point number. So basically, this vector of 1536 elements is the numeric representation of this sentence, that this is a simple query. Then we move on to prompts. So in prompts, we basically have LLM prompt templates, chat templates, example selectors, and output parsers. So LLM prompt templates, it contains basically a text string, and where it can also take in some variables, right, from the end user and then generate a prompt. So chat templates is basically adding the template prompt, right? The variables and so on to what we saw in the previous example. So basically can add the templates format to the system message, AI message, and human message. Then we have the example selectors. So in example selectors, what happens is You would have heard about the few shot learning, right? Where we give LLM a set of examples so that it learns from those examples and then gives a better output. So sometimes, and one of the biggest limitations that we have is, of course, the length of the prompt. So suppose we have the user enters a very long query, right? Then we need to kind of internally adjust the length of the example selectors so that the prompt tokens do not exceed the supported value. And we'll get into the output parsers in a bit. So coming to prompt template. So here I have given a sentence saying that I'm traveling to France next week. What are the best museum to visit at city? So city here is an input variable. So this is a template, and then you can construct a prompt template where we specify that the input variable is city, and then we give the template. And it's always, so by default, the validate template is set to true, but if you don't want it, you can set it to false. And then what happens is when the user enters the city Paris, so basically the prompt dot format, you set the city to Paris, and this is how the prompt will look like once that variable comes in. So what are the bit to visit at Paris? Then what we do is we run the LLM with this prompt and we get the list of museums there. Again, coming to the chat prompt templates, as I said, we can set a template for the system message, for the human message, as well as a template for the AI. So here what we are doing as, we are saying that we are trying to do a translation out here from English to French. And we want the response to be the English statement followed by the French statement. So again, we set all the messages and we run the LLM on that. And this is the response that we get. Now, coming to the example selectors. So here what we are trying to find is, get the opposites or the antonyms of the different words here. So we have happy and the output is sad, tall and short. So we have given 5 examples out here. And again, we first define a template, right? A prompt template where the input variables are, where the variables are input and output. And we have also given it a set of examples. And then there are various kinds of example selectors here. So the one that we have used here is something called the length based example selector. So depending on the length of the prompt that the user gives, the model or the prompt selector will, the example selector will kind of choose a couple of examples or all of the examples depending on the length. So here we give, the user gives a very short prompt here. His input is big, and then what happens is the length of the prompt or the input query given by the user is small. So we are able to include all the 5 examples. But if the user were to give a very, very long prompt, so this is, I've just made a very long sentence here just to show you that, because of the length of this input query by the user, we are able to include only one example. So this is what happens when you use a length-based example selector. So there are a whole lot of other example selectors also, right? So another one of them is we have something called the similarity example selector. So what happens out here is that the selector selects examples based on uh, it basically selects examples which are most similar to the inputs. So for finding the similarity, here it uses the semantic similarity, and this is done by with the help of embeddings, right? And then you create the embeddings of the examples, you create the embedding of the user input, and then basically it uses the cosine similarity to find the examples which match the best. It also uses a vector store. So vector store is nothing but a place where all these embedding vectors are stored. So I'll come into the details later, but for now, just understand that we are using something called phase. So again, as in the previous example, we have five um, examples of antonyms, and we are also creating a prompt template. And for as far as the example selector is concerned, we are using the semantic similarity example selector, and it takes uh, basically the examples, then the embeddings of the examples, and then there is a vector store that we need to specify, and this k equal to 2, that shows that how many examples which match or which semantically match the user's inputs should we pass on. So I'm just putting it as 2. So again, the user gives the input word as enthusiastic, and the semantic similarity example selector picks 2 examples from this list. So one is happy and the other one is energetic. So basically, it's able to understand that we are talking about emotions here, and it's kind of able to select 2 examples which again talk about human emotions. There are a couple of other example selectors also. We have something called a max marginal relevance example selectors, where the examples are selected based on a combination of which examples are most similar to the inputs, and while also optimizing for diversity, right? So, and again, we do have something called the n-gram overlap example selector. So it selects and orders examples based on which are more similar to the input according to an n-gram overlap score. So you can read more about them in the documentation, but basically, they all use a combination of similarity and also kind of optimize it for various other factors as well. And the best thing about LangChain is that you can create your own custom example selectors. So here I've just um, shown an example here, so you can create a custom example selector, which basically, inherits from the base example selector. And we can define a function called select examples, where inside this we can write our own logic as to, what kind of examples do you want to be selected. So here I have just written an example where we do a random choice of the examples. But basically it's up to you and your use case. You could select whatever you want. And I've just run this example as well. Now let's come into the output parsers. So you've seen that the language models output text, right? And many a times we do use them along with our custom data and custom applications that we have written. And we also want the output in specific formats. So this is where the output parsers come in. So again, you can look at the documentation because there are quite a lot of variety of out parsers here. And I'll just mention 2 of them here. So one is a comma separated list output parser. So if you set this output parser, what happens is that you get the output as an array which is comma separated. And then again, JSON is again one of the most popular forms that you want the output in. So we could use say the structured output parser to define a schema and then get the response in your required format. So here I've used and given an example of the structured output parser. So to use this, we need two things. So first is the response schema. So before I get into it, I'll show you how I need the answer. So whatever the user asks the question, I want a response which has two parts to it. So the output should be a JSON, and its first element should be an answer, which is the answer to the question. And I'm also interested in the source URL from which the LLM got that response. So to get that, we have to first do a response schema, and that should basically define what are the elements that you want in the response. And so you give a name to it as well as a description. Then you define an output parser, which is the structured output parser that we use here, and then feed into it the response schema. And then with that, you get the format instructions. So this format instructions has to be given to the prompt template, right? And along with that, as always, the other elements of the template remain the same, which includes the question and any other instructions or context that you want to give the user. Again, an interesting point to note here is that we specify the input variables as a question, and then we also provide the partial variables as the format instruction. So this basically comes in from the schema, and that schema converted, the output parser, which takes the response schema. Now, the third component is memory. So as I said, in chats, it's very important that we remember the previous interactions, both at a short-term level and at a long-term level. So there are whole lot of different types of memories which are supported in LangChain. I have given you a link there, but as far as the example is concerned, we'll come into it a bit later. Now let's get into the next part, indexes. So if you're planning to use any kind of external data out here, indexes become very important. So under indexes, we do have the retrievers, vector stores, document loaders, and text splitters. So let's get into them. So what I have done here is that if you look at the link that I've given here, you can find that there are a whole lot of document loaders available. Say, for example, you can load the data from a PDF file, from a CSV file. You can bring in data from Slack, from Twitter, everything. And what I've used here is I've used the Hugging Face dataset loader. So if you want to use a data set which is available in Hugging Face for your use case, you can use the LangChain document loader called Hugging Face dataset loader. You just have to specify the dataset name and which is the column that you want to access from this dataset. So for this example, I have just used the column called text, but basically you could use any of the fields that are of interest to you. So it's quite simple to use that data. You specify the data set name and you just have to load the data. And you get all the data in an array. So I'm just looking at one of the elements and it gives the text about a movie that is there in IMDb. So next comes text splitters. So typically when you want to use the data from a document or from a website, usually it will be huge. And then the LLMs have limitations in terms of tokens for the prompts. So to manage that, what we typically do is we kind of split this data, right? So whenever you have a PDF file, what happens is we load that PDF file, we kind of split that data, and the split data is what gets into the embedding. So we'll come to that in detail in the next example that we'll be using. But here what I want you to see is that, I've just used a very simple sample file. And again, there are a whole lot of text splitters which are available. But one very common one which is used as a recursive character text splitter. So it has got a multiple advantages. One is it uh, keeps the document format the same, as in it doesn't break words, right? And then it keeps all the paragraphs, sentences, and words together as long as possible. So what we do here is we read this file, and then I'm just printing out the first 100 characters here. And then what we do is we do a recursive character text splitter. So here I'm just giving the chunk size as 25 and the overlap as 5. So here what happens is it takes the first 25 characters, but if you see here, you will see that it is less than 25. That is because of the length of the next word. It doesn't break words. And again, we need an overlap because between the different chunks that you create, sometimes it's important that you need a context window. You need uh, a few words which are there as part of the previous chunk just to complete the semantic meaning here. So usually, chunk sizes of 1,000 and a overlap of 200 is usually common, but we might have to fine tune them according to our use case. So then we come into the vector stores, right? So vector store is like, we create the numerical embeddings, which is basically we encode the semantic meaning of a sentence in a vector, and we need to store this vector somewhere. So a vector store is where we can store the embeddings of these documents. And the best and another advantage of that vector store is that it provides fast ways to look up the relevant documents by embeddings. Then we have the retrievers. So retriever interface, it's a generic interface that makes it easy to combine the documents with the language models, right? So the interface exposes a method called get relevant documents, which takes in the query from the user, and then it returns a list of documents which are semantically similar. So we'll look at this whole index part in a separate example. But for now, what I want to show you is that there is something called a Wikipedia retriever. Suppose the user wants to get the Wikipedia page of some something in his query. Then what we can do is we just have to use the retriever called Wikipedia retriever, which is already built into the LangChain. And with just 3 lines of code, you will be able to get the data from Wikipedia. So this is quite useful, especially if you want to kind of provide a definition of something in your use case. And with that, we come into the chains. So we have talked about various components like LLMs, prompts, memories, indexes. So what chains allow us to do is it allows us to combine multiple components to create a single coherent application, right? So again, there's a whole lot of chains which are supported within LangChain. So the list is really, really huge. So that's why I provided a link here. And here what I will talk about is, one is the LLM chain. So this is the most common type of chain. So we have seen it in the example above, right? So what we did was we first defined a model, then we defined a prompt template, And then in some cases, we also provided a output parser. So these are all different components, and then we are kind of chaining them together in a sequence to give the user an output. So that is what is called a LLM chain. But and we will also be sorry but what we'll also be doing is we'll look through another example where we are combining the different components in indexes, right, to parts to load a document and get the LLM to answer questions from the document. So that's another example. But here I want to draw your attention to something called a load chain. Most of you would have heard about the Hugging Face hub, right? So similar to that, we have something called a LangChain hub. So I'll be providing the links to that in my presentation. So what happens is it's a repository of chains, prompts, and agents. So you could look through this repository, and if there is something that interests you, you could always use that. As in, you wouldn't want to waste your effort recreating that. So one piece of advice, before you come for the hackathon on Saturday, would be to go through this LangChain hub and see if you can, find something useful that matches your use case. Sorry. So here what I'm doing is I'm loading the LangChain package, and then I'm trying to load the LLM map. Right? So as you would know, LLMs are not good at performing mathematical computations. So we can use the LLM math chain, and then if you want to give, what is to the raised to 0.12, what happens is because this chain is used, LLM doesn't try to calculate it on its own. Instead, it uses the LLM matching and gives you a response. So next, we come into what is called the agents. So agents are kind of similar to chains in that we can kind of combine the components together. But in case of chains, the order is kind of predetermined, right? So it will do steps 1, 2, and 3. But if you want to take that decision based on the user input, then we need to use something called agents, right? And what agents do is that since the order is not predetermined, they use the LLM to determine which actions to take and in which order. And then agents have something called tools. So these are basically the custom code that we write, right? So that the agent can do the different actions. Then we have the toolkits. So toolkits are what an agent applied to a particular use case. So if you look at it in the link that I have provided, you can see the list of toolkits which are available. So let's get into an example, right? So basically there are two kinds of agents. So one is an action agent, the other one is a plan and execute agent. So this plan and execute agents are quite interesting because first they plan what to do and then they execute the different tasks, right? So here suppose you have a question called, who is Leo DiCaprio's girlfriend and what is her current age raised to the power of 0.43. So what we do here is that we kind of give it two tools. One is search and the other one is calculator. And then we kind of give a plan and execute to be true. So what happens here is that, let me just show you, because once we set the verbose to true, you can see that what are the different steps which are happening here, right? So what it does is it first does a plan and execute step, which says that, search for Leo DiCaprio's girlfriend on the internet and then the next step is to find her current age, and then raise that to the power of 0.43, and then output the result. And then once that is done, then it kind of gets into the agent executor chain. So one of the quite interesting things that I have observed when I've kind of worked on various use cases here is that once you have the plan and execute chain, you would be kind of able to um, refine your prompts based on how um, the LLM is kind of planning and executing it, and this would kind of have result in better results. And once this plan and execute step is completed, then it kind of gets into the executor mode, and then runs the different queries using the tools available on that, and then yeah, gives you a value. So then we have, let me also show you something called a conversation agent. So earlier I talked about memory, but I kind of did not give you an example of memory. So what happens is in a conversation, right, when you are chatting with a bot, you would have kind of given it some details. Let's assume that you are talking to call center, chatting with this thing, and you're telling about some problem in, say, some of your devices, and they would have asked, what is the model of the device, how old is it, is it under warranty or not. So all of that information. So the bot obviously cannot keep asking the user for the same information. It kind of needs to store that in memory and then reuse it. So this is where the concept of memory comes in, right? And so here you see something called a conversation buffer memory. There are multiple types of multiple types of memory which is available. So you will have conversation buffer memory, which kind of stores all the conversation. Then you have versions which store, the last, say, 3 steps, or say n number of steps. You could store the summary. You could store the summary of the previous n number of conversations. You could have a memory that would kind of store the different entities. So basically, it all depends on your use case and what you are trying to do. So here I have used a conversation buffer memory, and I'm using a chat open AI agent, and then I am initializing the agent here. I'm giving it the tools that it has. So basically, we give in order to for it to be able to search the net, we are providing a current search, and here we are giving a description saying that when this tool has to be used. So typically here the agent type that we are using is conversational React description, which is kind of tuned specifically for the chat, because the responses that it gives would be reformatted as if it's in a conversation. And then you have React, which is like it would kind of reason and then kind of act on that. Then you have zero shot agents. There are a whole set of these agents, so you can again look up the documentation for more details. So basically what happens here is we have initialized it, we have given it a memory, and the first um, input from the user is like, hey, I am Jane. So the bot responds saying that, hello Jane, how can I assist you? So the next question the user asks is, okay, who am I? Then the bot says that you are Jane. So basically it is this conversation buffer memory which stores this information for the um, for the subsequent conversations. Then we come to the last part, which is the callbacks, right? So again, there are multiple callbacks handlers which are available, and these can be used for logging, monitoring, streaming, and various other tasks. So, what you can do here, or what I've done here is that I have created something called a standard out callback handler. So, what this would do is basically it logs all the events to the standard out. So, this is exactly what happens when you set the verbose flag to true, right? So, typically when we run a chain, we kind of, or when we process something on the LLM chains, many times we set the verbose to true so that we can understand what is happening. And suppose you don't want to set the verbose to true, and another alternative is to use the standard callback, standard out, std out callback handler. So what happens here is it kind of puts in all the logs to your std out, which is basically your terminal where you're running. So the first part, we have given the number 2 and we have set the verbose to true. So what happens is it gives, the what is the prompt after formatting, and it gives 1 plus 2. And then here, we have not set the verbose to true here in this line. We are giving an input of 3. So what happens is it kind of provides the similar output as to the verbose equal to true, and then you get intermediate logging value, right? So there are a whole lot of handlers which are built in, but what you could also do is you could create a custom handler, and then depending on what you want to be logged and how you want to be logged, you can customize it. Now, we also have async callbacks, and we can also have multiple callbacks, yeah, or rather multiple handlers in a callback. So with that, we complete the various, modules that kind of make up the LangChain as of now, because there are like developments happening every single day. Okay. Let's now take a look at another example where we are dealing with only the index component, right? So what we are trying to do here is we are trying to get the LLM to answer a question from a PDF document. So for this example, what I have used is I've used the paper Attention as All You Need, where the whole journey started. And I am not using this from the URL. I am using it on a local version of this file. But this is basically a 15-page document that I am using. So again, if you come into it, you start with installing whatever the packages in Python that are required. Then we have the OpenAI API key. You can use them. And what I have done is I have uploaded this file attention.pdf into a folder called variables here. And then we load the document. So when you, and here, since it's a PDF document, I'm using the PDF loader in the document loaders, right? And then I check what is the length of the document. Then I find that there are, 15 different pages there. Then, as I said earlier, we need to kind of split this document. It's kind of too huge, 15 pages of data. We need to split it into more manageable chunks. So here I have given a chunk size of 1000 and the overlap of 200. I'm using a recursive character text splitter. And now when I split that, what happens is this whole one document, which had 15 pages, is now divided into 52 chunks. So let's take a look at the first chunk. So it says, the attention is all you need, and then it talks about the authors and so on and so forth. So now that we have read the document using a document loader, we have split the document. Next is to convert each of these chunks into embeddings. So again, for embeddings, we are using something called face here. So the you could use other versions as well, like we have the pine cone, or the VV8, or there are other options as well, right? But what I am using here is the face here. And so what and I'm using the OpenAI embeddings, so again, keep track of your usage once if you're using the OpenAI embeddings. So, and then comes the retriever module. So to the retriever module, what we are giving is that, so from the embedded documents, we are specifying that whenever the user uh, gives a query, retrieve k number of documents, which is 3 here, which kind of match your um, the query that the user has given. So uh, let's so um, I just went back to the document, and here if you look at it, and then I search for what was the data set that this whole attention model was trained on. So then there is some information saying that they trained it on the standard WMT 2014 English German dataset. So why I showed you this was the question that the user was trying to use, was trying to ask is, what data set was used. And then these are the responses that we get. So since we had asked the retriever to retrieve 3 different documents, you see that there are 3 different results which was given there. But the response, the source document over here is like the 3 documents are listed here. And then the first one is, of course, what we wanted. We used like, the larger WMT model, and so on and so forth. So that's what the response that we get. And again, the next question which the user asks is, who are the authors of Attention is All You Need? So again, the result is the different authors of this paper. So again, if you go here, you'll see that it picks up all the different names from this paper and returns to you, right? So this is how it works. So again, this is just a very simple example that I've given. It uses a PDF. What you could also do is use data from various other sources. So if you're planning to use external data, just go through the document handlers and then see what works best for you. And also this text splitting is quite important, and there are various text splitters, so have a look at them as well. So there is something else that I wanted to mention to you, and that is the Lang flow, right? So what we have done now, we have written the code, but if you want a UI to do all of these different steps that we have done, right? So where you create a LLM model, which is an open AI, you create a prompt template, then you kind of use create a LLM chain, and then ask it some question and then respond. You can use the Lang flow, which is basically an UI for LangChains. And then it has a chat window right at the bottom. You can click on that and then kind of give the queries and then the bot will respond based on whatever you have configured here. So the next is I want to kind of leave you with few of the things that I want you to try out. So first thing is the LangChain documentation has a whole section on use cases where they also talk about uh, the autonomous agents as one of the use cases, and chatbot is another. So just take a look at them and see if you can kind of use any one of them or if you want to. um, and it also includes something like summarization. Then if you want to query some tabular data, so all of these are kind of listed as use cases there, so please do have a look there. And again, as I said, I have used OpenAI embeddings and OpenAI models, but you can try out the various open source models as well. And then instead of OpenAI, you can try out other embeddings, right? So instructor is an example here again, which you can use. So which is basically an Hugging Face instructor embeddings. And then we used the face vector store, but there are options like BB8 and Pinecone. So Pinecone basically, I think if you create a free account, you would have a certain quota allocated to you for creating the vector store. Also check out the LangChain hub, right? So, and if you can reuse any of them, that would be good. Again, I want to leave you with some of the references and the learning resources which I have used. So do subscribe to the LangChain Discord channel. And then there are a couple of very interesting YouTube channels where there are awesome videos about LangChain. So data independent, then James Braid's prompt engineering. These are some of the YouTube channels that I follow and which I have referenced for creating this session. And also, if you're interested in using the GUI for LangChain, do check out the LangFlow. So there's a very interesting article by Grayling in Medium where he has written about the LangFlow. So please do check out that also. To install LangFlow, basically you have to go to the GitHub of LangFlow, and it's just two steps installation for that. So I think that with that I come to the end of my presentation, right? And so good luck with the hackathon. But as Nitin Agarwal, who is the head of cloud AI services of India in Google says, you can do anything based on your creativity, but keep a check on your enthusiasm because Gen AI can overwhelm you very fast. And I'm sure many of you might have experienced that, but it shouldn't be a deterrent. So see you all on Saturday. Thank you.